We're looking at coordination compounds. We can have different coordination numbers depending on how many ligands are bonded to the metallic center. If two ligands are bonded to the metallic center, that will be a coordination number equal to 2, and we will have a shape that is linear. When the coordination number is equal to 4, we'll have a shape that is square planar. And the coordination number is 4. It means that there are 4 ligands bonded to the metallic center. And then the last one is when we have a shape that is octahedral, and that will happen when 6 ligands are bonded to the metallic center, which means that we have a coordination number that is equal to 6. So we're going to be looking specifically out of these 3 possible configurations to the octahedral complexes. So we're going to review some things first. First, I want to review the orbitals. Okay? We're looking at transition metals forming these complex ions or coordination compounds. Transition metals are transition metals because they do have electrons in the d orbitals. When you have d orbitals, right, starting in energy level 3, we have always 5 d orbitals. When it's an s orbital, it's always 1 of them. When it's p orbitals, we always have 3 of them. And then when we have d orbitals, like for transition metals, we will always have 5 of them. We call these d orbitals degenerate when they have the same energy. When you have a metal, a pure metal, a free metallic element, your d orbitals are free. There's nothing bonded, or the only electrons that are in those d orbitals are the electrons from the metal. So in that free metallic element, your d orbitals are degenerate. They have the same energy. But when we start bonding ligands to that metallic center to form these complex ions or coordination compounds, now those d orbitals, they're going to split, which means that now they don't have the same energy. So you see at the bottom of the page on the left side, I have my 5 lines, each one representing each d orbital. All of them are aligned because they are representing the d orbitals for a free metallic element, and they are degenerate. They have the same energy. Now on the right side, I still have 5 lines, but I have 3 lines on the bottom part and then 2 lines above them. That means that those 5 orbitals now, their energy is being split because that's happening when ligands are bonded to the metal. When you have ligands bonded to the metal, now your orbitals are not degenerate. They will have different energies. You have 3 orbitals with the same energy on the bottom part, and then you have 2 orbitals on the top part that they're going to have a higher energy. Okay? So your 5 orbitals are split 3 and 2. 3 on the bottom, 2 on the top part. So all 5 of them are still d orbitals. Okay? It's just that now they don't have the same energy. This is happening for octahedral complexes. Everything that I'm going to do from now on, it's for octahedral complexes. If it's square planar, you will have a different splitting. Okay, it's not going to look exactly like this one. The orbitals are not going to be degenerate for square planar either, but the splitting is going to be different. Now, that splitting, right, where you have your 3 orbitals and then above them you have 2, the difference between them, we use a delta sub 0, and that's the crystal field splitting energy. So the difference between the amount of energy that you have on the 2 orbitals and the amount of energy that you have on the three orbitals below, the difference between those two energy is that delta zero. The magnitude or how much energy is that crystal field splitting energy, that amount of energy is going to depend on the ligands and also the charge of the metal. So we're going to look at those two options in a little bit. The crystal field theory, or CFT, is the name of the model that we use to explain the bonding between that metallic center and the ligands. And that crystal field theory that explains the bonding, it's what we use to explain that crystal field splitting energy, or that amount of energy that you have between the orbitals, the splitting in your d orbitals when the ligands are bonded to the metallic center. Since the splitting of the orbitals, right, is going to depend on which ligands are bonded to the metallic center and the charge of the metal, right, we do have what is known as the spectrochemical series. And in that spectrochemical series, what we have, it's a list of ligands that it's in an order. And we can actually use that list to determine if the splitting is larger or smaller. So you have the list right here. That's the spectrochemical series. Is this list that I have here. So you have different ligands listed there and they are in order. I have highlighted in blue the ligands that are strong field ligands. They are classified as strong field ligands because they will cause a large splitting in your d orbitals. Now, the ones that are highlighted in the purple color, they are classified as weak field ligands because they will cause a small splitting of your d orbitals. So the ligands that are causing a large splitting are the ones highlighted in blue. So I'm making a representation. The splitting of your d orbitals is still 3 on the bottom part and 2 on the top part. That is not changing. It's the same for your strong field ligands and weak field ligands. What is different is the distance between those orbitals. And that distance between the orbitals is your crystal field splitting energy. So the larger the distance, the bigger the amount of energy. The smaller the distance, the smaller the amount of energy. When you have a metal, okay, and the metal you have, it's bonded to a specific ligand. Now you have another complex with a different metal with the same ligand as the previous one. The splitting now is not going to be determined by the ligand because you have two metals and different metals and they're bonded to the same ligand. So the splitting now is going to be determined by the charge of the metal. So you need to remember that the higher the charge of the metal, the larger the splitting. When you have the atomic size, right? The atomic size is determined by the distance that you have between your positive nucleus and the valence electrons. Now, when you have something with a charge, like in this case, we're looking at the metals. Okay? Metals are always forming ions with positive charges. They're giving electrons away. So when the metals are giving electrons away, right, now that distance between your positive nucleus and the electrons starts decreasing because the metal is giving away valence electrons, which are the ones that are farther away from the nucleus. So the size of your metal is going to decrease as the metal starts losing electrons. So the larger the positive size of the positive charge of an ion, the smaller the size. When you have a smaller metal center, it can pull the ligand strongly, which is going to cause your orbitals to feel a larger repulsion and the splitting will be larger. That's why when the charge of the metal is increasing, the splitting or that separation between your d orbitals it's also increasing. They're going to feel a larger repulsion between them because your positive metal will be pulling those ligands stronger than a metal that has a larger size. So we're going to look at this both options, right? The splitting can be determined by the ligands or by the charge of the metal that you have. So I have two examples, one for each one. I have my spectrochemical series here again, so we can easily look at it and find out which ligands are giving a strong field or a weak field. So we're trying to determine, we have a pair of complex ions, and we're going to be determining which one has the larger splitting in the d orbitals. So for number one, I have two metals, right? I have iron with water as a ligand, and I have chromium with water as the ligand. So you have two different metals with the same ligand. So we cannot use the spectrochemical series to determine which one is going to have a larger splitting because you have the same ligand. It's water for both of them. Water, it's a weak field ligand, right? So if it's a weak field ligand, it will give you a small splitting. That's how it works. But since it's the same ligand for both of them, we cannot use that to determine which one is going to have the larger splitting. So for this specific example, we have to check the charge of the metal. When you have a different metal and the same ligand, to determine which one has the larger or the smaller splitting, you have to determine the charge of the metal. That's why we learn how to assign the oxidation number for the transition metals when you have a complex ion. So checking the first one where I have iron. Water is a neutral compound, which means that the charge for the water is 0, right? So you have an overall charge that it's 2. So you have 6 waters. Those are the ligands. Each one has a charge of 0 because water is neutral. So that will give you 0 right here, which means that the charge of iron in that complex ion is positive 2. And then we are going to calculate the charge for chromium on the second one. So you have 6 waters, each one has a charge of 0 because it's a neutral ligand, and you can actually use the spectrochemical series to determine the charge of your ligands. Okay? I have CO, it's neutral, Cn, it's -1. This is nitrite, you have a -1. You have ammonia, which is neutral, water, which is neutral. So you can actually look at the charges in that spectrochemical series. Remember, you have a short list of ligands. So in the spectrochemical series, you have many others, and there are others that I didn't include here, but the ones that we're going to be using, they're part of this shorter version of the spectrochemical series. So I calculated here the charge for chromium, and we have a +3. So now you have 2 different metals, the same ligand for both complex ions. You determine the oxidation number, and this is the proper way of finding which one will have the larger splitting. So you have that for iron, oxidation number is +2, for chromium is +3, and then you have a note right there that is telling you the larger the charge, the larger the splitting. So out of the two, the metal with the larger charge or larger oxidation number is chromium, which means that that one should be the one with the larger splitting. So for the first pair, I'm marking that one. Now for the second example, you have the same metal, okay? You have iron for both complex ions, but you have different ligands. Okay? So when you have the same metal and different ligands, you can actually look at the spectrochemical series to determine which ligand is strong field, which is going to give you a larger splitting, or if you have weak field ligands, and you can use the spectrochemical series just to find out which one has a larger splitting. The closer the ligand is to the left side of the list, the larger the splitting. Okay? So we're starting with CO, which is carbonyl, and CN. They have about the same amount for the splitting if those are the ligands. So I have CN, the one on the left, and then in the other complex ion, we have water here. Cn, I marked that one in blue because that's a strong field ligand. And then for the water, we have a weak field ligand. So since Cn it's towards the left side of my list, it means that it will be a strong field ligand, which is going to give you a large splitting. You have water, which is a weak field ligand, and that one will give you a small splitting. Since we're looking for a large splitting, the one that has a strong field ligand will have a larger splitting than the one that has a weak field ligand. But we can also compare compounds with weak field ligands, both of them. You can have iron with Cn, and you can have iron with NH3 instead of water. Cn is further to the left, which means it's stronger than NH3. Okay, it's not just that we can compare strong field ligands with weak field ligands. You can actually compare 2 strong field ligands or 2 weak field ligands. The strength, right, is decreasing as we move from left towards the right side. There are two things that we're going to be looking at for these coordination compounds. We're looking at the relationship between the color of these complex ions and the crystal field splitting, that amount of energy that we have when the d orbitals are splitted because of the addition of the ligands to the metal. So let's review some things. Okay, the color of an object, right? It's related to the absorption or emission of light. The electrons can move between orbitals. For the electrons to move between orbitals, they have to absorb energy. Energy can be absorbed as heat, as light. For an electron to move from a low energy level to a higher energy level, it has to absorb energy. When the electron goes back down, it will emit energy. And again, absorption can be heat, light, or any other source of energy. And for emission, the same thing applies. Okay? If it's light, what it's being absorbed or emitted, if that light is in the part of the electromagnetic spectrum, which is the visible part of that electromagnetic spectrum, we can actually see a color. Okay? So color is related to electronic transitions. So what I have here is that part, visible part of the electromagnetic spectrum. Something very, very important is the relationship between energy and wavelength right here. That symbol right there, lambda, is the symbol for wavelength. The higher the amount of energy, the lower the wavelength. Remember, the splitting between your d orbitals, that's an amount of energy. The larger the distance between your d orbitals on the bottom part and the ones on the top part, the larger that distance means that the amount of energy it's bigger. So if something is absorbing energy with a wavelength. Look at the wavelength that I have listed here. I'm doing this from 700 nanometers, that's wavelength, all the way down to 400 nanometers. Okay? So you see that the wavelength is decreasing when we go from red down to the violet color. The amount of energy is increasing as the wavelength is decreasing. That's the relationship between wavelength and energy. They are inversely proportional. So now your wavelengths are related to the colors, and the colors are related to the amount of energy. So I have here, I'm looking at this diagram right there. Is the same that I have in my list right here. It's a different configuration, okay? Because when I have my diagram, like the hexagon right here, we can actually look at color, which is related to wavelength, okay? And we can relate that amount or wavelength that is being absorbed with the color that we can observe. So I have a note right there, absorbing orange. If you have a solution and that solution absorbs where you have the orange color, which is between 600 nanometers and 650. If a solution is absorbing any of those wavelengths between 600 and 650, the color that you observe for that solution will be the one that you have on the opposite side. which is blue. So if you have a solution that looks blue, you can see that it's blue, a blue solution. You can measure the absorbance for that solution. You might see different peaks for the absorbance value, but the largest one will happen at a wavelength range between 600 and 650. So my diagram, the one with the hexagon shape, can actually let you see, depending on the color that you observe, which wavelengths can be absorbed by that solution. If you have a solution that the color that you get to see, okay, the one that you're seeing, it's yellow, it means that that solution will be absorbing light with a wavelength between 400 and 450, which is what you have on the opposite side of this yellow color. 400 and 450 corresponds to a violet color. So that's how we use this hexagon here. Depending on the color that you get to observe, you can find out the wavelength, right? Wavelength range that that solution will be absorbing. Another thing, that color is related to an amount of energy. For example, a solution that is absorbing between 400 and 450, it's absorbing a lower wavelength, at the lower wavelength range, right? It's the lowest one that we can get because the amount of energy is higher. The higher the amount of energy, the larger the splitting. That's how we're relating amount of energy with the splitting and the colors. So at the bottom of the page, I have very small right there, the spectrochemical series with all of the ligands, so we can refer to that when looking at our ligands in this example here. I have two solutions. Okay? I have a solution that I get to see that it's yellow and a solution that I get to see that it's green. And I have two compounds. Now, out of my two compounds, I don't know which one corresponds to the yellow solution and which one corresponds to the green solution. So to determine or to match these solutions here, the yellow and the green, with my two compounds, the two that I have listed there, we have to find out the color that it's absorbed, how that color it's going to give us an amount, not a specific number for energy, but it's related to amount of energy. And then we can relate that to the splitting depending on the ligands that we have. So I have my two compounds right there. I have M that represents metal, right? That's why we use an M. It's a metal. It's the same metal for both of them. So my ligands are Cn and water. So Cn is a strong field ligand. I'm going to mark that one with a blue color, and then the other ligand is water, which is a weak field ligand right there. Now let's look at the colors. I have a solution that is yellow, and if it's yellow, that's the color observed, and that will be absorbing. And the other one, color observed, it's green and absorbing. So pause the video so you can try to find out which colors are being absorbed or which wavelength it's being absorbed. So when you have a yellow solution, right? The yellow solution, that's the color that you're observing. And if you're observing yellow, it means that the color that you have on the opposite side of that yellow color is the one that is being absorbed. So that yellow solution will be absorbing violet in that range of 400, 450. For your green solution, the color that you have in the opposite side of that green color that you're observing, I'm starting right here, is the red one. Red between 650 and 700 nanometers. Okay? So that represents the wavelength. So now these colors, right, are related to amount of energy. And the amount of energy is related to the splitting. So I have the violet color as a larger amount of energy related to it. You can look at that in the sketch that I have right there, where I'm starting in red, orange, yellow, going all the way to violet, and it's telling you increasing energy as you move from the red towards the violet, right? Increasing energy, decreasing wavelength. So you have a smaller wavelength range or smaller wavelengths for the violet color, 400 to 450, because that one has a higher amount of energy. So now we can look at the splitting. You have your two ligands, CN, which is a strong field ligand, giving you a large splitting. A large splitting is related to a large amount of energy. So out of my two options, the one that has a violet, absorbing violet, means that it will have a larger splitting because you have a larger amount of energy. So we can match this, my two ligands, CN, it's a strong field ligand, and that one will go with letter A. And then green, which is the observed color, it's absorbing in the red area, and that's a larger wavelength, right? You have 650 all the way to 700, which means that that's a smaller amount of energy. Since you have a weak field ligand, which is the water, right? Weak field ligands, they have a smaller splitting. So this one here corresponds to the green solution. So I have here two problems for you to solve. The first one, it's asking you for which one out of the three complex ions that you have listed there will absorb light of the longest wavelength. Okay, so which one is absorbing light of the longest wavelength? You have to relate wavelength with energy and amount of energy with the splitting depending on the ligands that you have. Now for the second one here, you are matching, okay? You have three complex ions on the left, and then you have information on the right side. A red solution that is absorbing at 523, a green solution that is absorbing at 695 nanometers, right? A blue solution that is absorbing at 647 nanometers. So you have wavelength, relate that wavelength with amount of energy and amount of energy with the splitting in your d orbitals for each different ligand that you have in those three complex ions.